We should be on this page. I broke mine up into several other pages, so we're starting with dynamic balance. Sometimes when we had the same beaker size, we would end up with the same amount of water. Should have ended up with the same amount of water. We had a little bit of spillage going on, so we didn't end up exactly. But we should have ended up exact when we have the same amount going backwards and forwards. Okay? But if we start at different places and we have different size beakers, in other words, some reactions don't go all the way to completion. Some reactions aren't like combustion, where I have a big explosion and I'm done. Some reactions go forward, and when so much gets in the product, it starts coming back. So I end up having a reaction where some of it's coming back. And when I hit to the point where my reactants and my products are staying steady and the amount being transferred back and forth is the same, then I reach what's known as dynamic equilibrium. So on this graph, this was where on this graph I would hit dynamic equilibrium. On this graph, it's when I start flattening out that I've reached dynamic equilibrium. Okay, so you need to state or put on your graph somewhere like that. Now, we had reached at some point right here where they actually had the same amount in each container. Even though one started small and one started big, there was a point at which the concentration or the amounts were the same. That doesn't mean dynamic equilibrium. It just means I had the same amount for a second. And then it kept going, and I would not be at equilibrium until, dynamic equilibrium, until I reached the point at which they were the same. Okay, so we showed on the graph where the dynamic equilibrium is. Now, instead of just like we've been doing, putting one arrow going one way, we now do a double-sided arrow. So this double-sided arrow tells me that the reaction can go both ways. A lot of times they'll do, it mostly goes this way and a little bit comes back. Or they can go, a little bit goes forward and a lot comes back. So they show you about what's going on, who gets the small beaker and who gets the big beaker kind of thing. Okay? So go on forward, it's down on your thing here. We also start talking about heat being added into the equation. Now, heat can be added in the equation like this, or I can actually have it be outside the equation and be called delta H. In this one, delta H could be like a positive 30 kilojoules, and I could put it outside the equation. Or delta H for the bottom one could be like a negative 30 kilojoules. It can also be put into the equation right here, so I could put 30 kilojoules here, and I could put 30 kilojoules here. The negative and the positive right here, those just tell me what side of the reaction they go on. Positive means I have to put it into the reaction to get started. Negative means it gave it off. So the thing here is to know where my heat is. Is it reactant or is it a product? Okay, that's the important part. You really need to know that. And you remember, if it was added in, then it was endothermic because I added heat in. And if it came out, it was exothermic. Okay, so we need to make sure we remember those words, vocabulary. All right, so in our bucket demo that we just did at the very first, we were transferring water back and forth. And as long as the beaker sizes were the same, we should have ended up the same amount of water on both sides because you were transferring the same amount. Okay, so if when I had, in one side I had a lot of water and the other side I didn't, even when we had the same beaker size, it still would level out, right? But when I traded beaker sizes, what happened? Well, the side that had the little beaker trying to transfer always ended up lower, right, than the side that had the bigger beaker. So let's see if we can answer these questions. So what happens to the large buckets? So what happens to the amount in the larger buckets? So when I had the larger bucket moving, or the larger beaker moving stuff, that bucket became small. When I had when the transfer containers are changed, when I changed to small, let's try this again. The first one, our beaker sizes were the same, and it didn't matter what side of the buckets here was big. We'd end up at the same. Here, when I changed the beaker sizes that were moving the water, okay, then if, I don't really want to say large bucket here, it would have been large beaker. On the large beaker side, the water got lower. On the small beaker side, it got higher, right? Okay, when the transfer reaches dynamic equilibrium, what's true about the amount being transferred? We just did this. They're equal, okay? Jacob, you were getting this down? It's all right. I feel that way too because it's Friday. I'm going to try and keep you focused here. Okay, so then we come to what's known as Le Chatelier's principle. Make it green. Okay, Le Chatelier's principle. We're talking about what happens when I do something to one side. So I think about when I was growing up, we moved to a new house and there were holes in some areas and there were piles in other areas of dirt from the people building the house, and we had to level it all out. So if there was a hole, we had to move things into the hole. If there was a pile, we had to spread it out, right? So if I add something, that's like making a pile, and I've got to spread it out. I have to shift it away from one side to the other. So remember, we have reactants on this side, and it goes backwards and forwards to products. So if I have a pile on one side, I've got to shift it to the other side. So adding reactants would shift it which way? Right. So shift right towards products. Okay, what if I dig a hole at the reactants? So I would shift left toward the reactants. What about removing the products or making a hole on the product side? Yep. Shifts right toward products. What about adding products? Shifts left towards the reaction. Towards reactants, I should say, not reactions. Okay, and then we also got other things that will affect it is temperature and volume. Now temperature, if you remember, if it's endothermic, where was it when it was endothermic? Where was the heat? What was endothermic?
It's when it's going in.
So it was on the reactant side, right? And when it was exothermic, so you treat this just like if it was, you treat this just like it was up here. But you just need to know if heat's on the reactant or the product side, just like I said on the slide before. Okay? Then we get a little tricky. Pressure and volume. Okay, so this one has to only do with gases. It doesn't care about liquids, it doesn't care about solids. It cares about gases. So let's take a reaction that we know really well. H2 gas plus O2 gas yields H2O gas. Is it balanced? What do I need to do to balance it? Yep. Okay. So, Thomas, how many gas moles do I have on the left side? How many do I have on this side? How many moles of gas? I have 2 hydrogen and 1 oxygen for a total of 3. Okay? Ian, how many do I have on the left? Or right? Sorry. How many? How many? Help him. How many? I just have 2. This is what we balanced with. numbers we balanced with. So I have 2 plus 1 is 3, right? And I have 2 up here is just 2. So I'm just looking at the moles of gas. So I'm just looking at the numbers I used to balance the equation in front of the ones that are gas. If it's a solid or liquid, I ignore it for this, okay? So I'm just worried about the gases. Now, think of a pop. When you open a pop bottle, what happens? So what's happening? It's releasing gas. So what did I do when I opened the pop bottle? I released the pressure. So I made the pressure lower. What happened to the gas? It came out, right? So when the pressure's low, I want to go to the side that has more gas. When the pressure's high, I'm going to go to the side that has the least amount of gas. Now think of the bottle. It was a small container, and when you open the lid, you now made it a bigger container, right? So if I'm in a bigger container, or bigger volume, then I have a lower pressure. If I try and squish that thing down, I'm going to increase the pressure, okay? So I'm going to ask you a question. You tell me what side it's going to go. Remember, this is the reactants, and this is the products. Okay, I have just decreased the volume. Which way is it going to go? Decrease the volume. Which way is it going to go? Which side? Show me with your fingers so I know everybody's participating. Just decrease the volume that this thing's happening in. This reaction's happening in. So I have a closed container and now I've squished it. I'm going to go to the product side, the side that has the least amount of gas. So if I'm increasing the pressure, the gases don't like to be in high pressure, so they go back into the water or whatever's with them. Okay? All right, so here's another question. How about I increase the pressure? Show me with your fingers which way it's going. Not all are participating, and I need everybody to participate. So I've increased the pressure. Increase the pressure, less gas. Okay? So decrease the pressure, more gas. Decrease the volume, less gas. Okay? Increase the volume, more gas. So let's write this down. So we have, let's do it this way. Increased pressure, decreased volume, goes to side with less gas. Decreased pressure or increased volume, they don't have to do the same, goes to side with more gas. I should put moles. Okay, does that make sense? Okay, let's try this on an actual equation. So this equation should be written. We couldn't find the actual, this arrow should be like this. Okay, but we're going to take it, be that way for a minute. Okay, before we even do anything, let's talk about some real quick. Let's look at how many gases we have. Let's find the heat. Let's do everything we need to do to maybe answer some questions. So how many moles of gas are on my reactant side? 4, good. 3 plus 1, so we have 4 gases over here. What about on my product side? Good, 1 and 1, that gives me 2 gases. Okay, where is my heat? The end, this number right here is my heat, right? So it's exothermic, so I treat heat like product. All right, so let's go and do these questions. If I add CO2, that's like I'm making a pile on this side. What do I need to do to make it better? Shift right away from it toward product. Okay, next one. So, whoops, I forgot to show shifting up here. So it's going to go that way. All right, so if I remove H2, that's making a hole here. What way is it going to shift? Good. Shift left toward reactants. So it's going to go that way. All right. How about if I add H2O? Okay, everybody show me with your hands. Which way is it going to go? So I'm now putting in H2O. So I'm making a pile here. So like the dirt that I was talking about at the beginning, and I need to spread it out. So I have more water, so it's going to shift towards the reactants. Okay? So if you'll notice, if I'm going this way, it shifts this. If I'm going this, see how the arrow just continues? If I'm shifting, if I'm going this way, it just keeps going this way. Okay, see how it sort of works that way too? So you can look at it two different ways. So you can look at it like I was telling you before, like when we moved in the new house and we had a pile, we had to spread it out, or I had a hole and I had to fill it. Or you can look at it this way, saying if you do the arrows always facing down and the ones on the top I'm putting in and the ones on the bottom I'm taking out, the arrows have to still face the same direction, still go the same direction. Okay, so here we're going to remove CH4. I'm going to take that out. There's a hole. I got to fill the hole. Which way is it going to shift? Towards the products. Good. So shifts right toward products. Grace, are you getting this? Okay, so I can look at this another way. I put the arrow down because it's taking it out, right? So the arrow crossing this arrow in the equation has to go the same way, so it has to go that way. It couldn't face the other way because then the arrows will be opposite each other, right? If I take something out, I'm making a hole. And to get back to equilibrium, I've got to fill that hole and make it easy. It's like doing a teeter-totter where one side we were equal, and then I took something off one side. Well, if I took something off, somebody had to go home. I have to shift somebody from the other side over. Does that make sense? Okay. All right, so let's do the next one here. I've got to pick another color over here. We'll try purple. Okay. I'm adding pressure to the system. What is that going to affect? Thomas? I know you're dozing, dude. Okay, you got to stay with me. Okay, I add pressure to the system. What's going to happen? Jade? I'm adding pressure to the whole system. I'm adding pressure, so I'm adding pressure by either decreasing the volume or increasing the temperature, something I'm doing to add more pressure. Side that has less gas, because more pressure, less gas, takes less room up. So I'm going to go shift, which way? Okay, you guys should be writing this down because you got a whole thing that you're going to have to look back and see what happened to this. Toward products, right? Okay, we're picking another color. I'm going to say orange. Add heat. So I'm adding heat. Treat that just like we did any of the others up top. It'll shift towards the reactants because it's got to keep going the same direction, so it's going to go that way. Does that make sense? Okay, so shifts left toward reactants. Yep. Yep. Okay. Right. You just can't say reactants because it doesn't really just make reactants. It's just a shift. It's like somebody comes up and I'm standing here and somebody pushes on me. I'm going to shift to make sure I don't fall, right? I'm still standing. I hope I'm still standing. Okay. All right. Do we understand this? Yes.
So, if we remove something from the product side, then it
Goes
goes to the reactants, and if you remove
Nope. If I take something out of products, I made a hole, so my whole reaction is going to shift towards my products to try and fill that hole. If I put something in my products, then it's got to relieve that pressure. I put stuff in on this side, so it'll shift to my other side. So this is where I put up front, up top. That's why I do this on top when I'm putting in, and then I know what side to go to because it goes away from it. And when I take out, I'm making a hole, so I shift towards those. So see how I always put my arrows facing down? If you just remember that, it makes it easier. Okay? All right, so going forward, one more page.
oh, we can do assignments.
End of rate notes. Stop. Study. Okay.
Why do they have 4 fingers?
I don't know.
The real question is like.
Yeah, well, he's, whatever. Okay, so what I want you to do right now, you've got all the notes that you need. Let me tell you what's going to go on here because I see you guys on Tuesday, but I won't be here on Thursday. Okay, and then you come back and, let's see, we have Monday, Wednesday, Thursday. So you guys take the test on Wednesday. Okay, so I will be here on Monday. You've got all the notes you need to do all your assignments. You're going to get an extra review assignment while I'm gone because the third term test is going to be mostly rates, but it's going to be also some review prop questions. So you have your review you've already been given. We're going to give you one more because it's starting to get down to SAGE time when we have to take that test. You've got to remember all that crap. Oh, sorry, all that good stuff, and we need to make sure that we understand it. So what I want you to do, I have not graded the labs that are in there, and the reason why I didn't grade them is because I wanted to make sure that you have done the best that you can do on these. These are worth 200 points, the lab we did last time. You need to make sure you have 3 sentences in your conclusion. You need to make sure that you've added an error analysis to each experiment, including overall. Okay? 4, 5, Thomas, and 6, put it away, are on the very, very back page of your lab. Don't do them, cross them out. They actually were an oops from another lab that I should have taken off. So 4, 5, and 6 on the very back page, yep, right here. So the container and the 4 and 5 down at the bottom, but you do need to do everything else. And the overall conclusion, you should do an overall error analysis. Okay, so that's why I left them in there. I did not touch them because this is one that we have to grade according to the district's rubric, and it's a little strict. So make sure everything is just perfect. Okay, use the colored pencils, make your graphs really nice. So you're going to have the rest of the time today. You've got plenty of time to get all your worksheets done and everything else because you'll have, we've done with everything. And we've got, what, Tuesday, Thursday, Monday next week, or the Monday of the next week, and then we have a test. So we've got 3 days that we can finish everything else up. Okay? Yes, ma'am. Okay, yes. I don't know. It depended on the legislature. But you got to do your best. Okay? I don't know. I don't know what I ended up finding out. We'll find out right before the test. So you gotta try your hardest, do your best anyway. You don't want to be compared to other schools and say this is the dumbest school, right? Because that's what they do. The district uses it to compare schools to other schools. So we want to be smart and push it through, right? Okay. All right. That's it. Happy with